This is another 2D support reactions problem. Here we have this yellow bar that is supported at point A by a hinge and at point B by a cable that's anchored into the wall. And we're given what the angle of this cable is relative to the bar. And we are asked to draw a free body diagram, calculate the tension in the cable, and then calculate the reactions at point A. All right, let's do that. Let's find our free body diagram. Well, to do that, we need to first get a concentrated force out of our setup here. And to do that, I think we'll take this and split it into two parts. Our distributed load. Do it like this. We will say this is part 1, this is part 2. So then we can say that R1, right, that's just a rectangle then. That would be 9 meters times 10 newtons per meter, or 90 newton. Then we can say X bar 1, now this is a rectangle, so it's just 1/2. 1/2 times 9 meters times 10. What am I doing here? I'm not doing the triangle. Just doing 1/2 of that. Getting ahead of myself here. Right, and so that, of course, is then 4.5 meters. Now, our moment from the first one would then be X1 bar times R1. And that would be 90 newton times 4.5 meters. And I did not calculate that beforehand, so let's do that real quick. That'd be 90 times 4.5, 405 Newton meters. That would be our rectangle. Now if we're going to look at the triangle on top, then we can say that would be R2, so that would be 1/2. The length is still 9 meters times 9 meters, and the height now is just this part right here, right? This is the height. So we have 30 meters, 30 newtons per meter minus 10, so 20 newton per meter. So that would be also 90 newton, right? 1/2 times 20 is 10, so we get 90 newton. Now the location, it's a triangle, so it's 2/3 from the tip. So that would be X2 bar would then be 2/3 times 9 meters. And that is 9 divided by 3 is 3 times 2 is 6, so 6 meters. And then our M2 is X2 bar times R2. So that will be 90 newton times 6 meters. That'd be 540 Newton meters. All right, 6 times 9 is 54. Yeah, sounds about right. So then, if I want to get the overall R, all right, that's just R1 plus R2. Be 90 Newton plus 90 Newton would be 180 Newton. That's an easy calculation right there. And then my X bar would be M1 plus M2 divided by R. So that would be 405 Newton meter, plus 540 Newton meter divided by 180 Newton, and that gives me a location of 5.25 meters. All right, so now I know I can replace my distributed load here. Now, if I want to draw my free body diagram, right, I have to get rid of all the supports. So I have to get rid of my hinge at A and my cable at B. A hinge has two support reactions, right? Two unknowns, in the x direction and the y direction. Remember that if we have a hinge, we can't pull it up or down or left or right. So that's kind of what the restraints are there. So let's draw our bar, something like this. We said we have the two support reactions at A, so A Y and A X. Again, we can draw these in for a hinge in any direction that we want to. For the cable that we're going to cut, we should have it as a tension because the cable has to be tension. So that would be TB. And of course, we also have our resultant force right here. R equal to 180 Newton, and we know that this distance here is 5.25 meters. Also know that we have an angle here that is 55 degrees. All right, then last thing here, X and Y coordinate system. And with that, I think we have all we need. We'll also put in A and B. A and B. So with that, I think we have what we need here. So then we need to get the tension in the cable. Let's do that on the next page here. B, finding the tension in the cable. How do we best do that? Right? We want to make sure that we don't include a x and a y in our calculations, right? We could just write three equations and then solve them one by one. But if we're specifically looking at TB, then probably the best thing for us to do is to do a moment around A, right? Because if I do a moment around A, then AX and AY don't come in. So let's see, that will be, we say moment about A is supposed to be 0. And so we can start with our distributed force here, our concentrated force. So that would be 180 Newton times 5.25 meters, and it's turning clockwise, right? This is how it's turning. So it means minus 180 Newton times 5.25 meters. And then B, let's divide this into its two components, right? This component won't have an impact, so that would be T, oops, not F, but T. TBX and T, I keep on doing F's here, not T's. TBY. TBX doesn't have a moment arm, right? Because the line of action goes through A. So all we have is TBY. Let's go back to black. And it is turning, if we think about A, right, it is turning counterclockwise. So plus TBY, and the overall length of this bar was 12 meters. Times 12 meters. All right, now let's see. We just write that again, 180 Newton, 5.25 meters. Now, what is TBY? TBY is equal to TB times, that's that component, it's the opposite leg, so it would be times sine of 55 degrees times 12 meters. That means if I solve for TB, I would bring that over, so it'd be 180 Newton times 5.25 meters divided by 12 meters times sine 55 degrees. Let's have a quick check on units. Yeah, the meters cancel out. I'm left with newtons. And as a value, I get 96.136 Newton for my TB. And of course, it comes out positive because we already know that it has to be a tension. If we would get a negative value for TB, then we should go back and check because there's something wrong. All right, then C, calculate the support reactions at point A. Let's go to our free body diagram. So we want to get our reactions right here. Now, the first one we can do of course sum of forces in the x direction. That will only have one unknown in it. Sum of forces in the x direction is equal to 0. Is equal to, well, we have AX going to the right, so we set it as positive. AX, and then we would have TBX also going to the right, so also positive. Plus TBX. That would mean we get AX plus TB times the x component is the adjacent leg, so cosine of 55 degrees. That means AX is equal to minus TB times cosine 55 degrees, which means if we plug in the values, I get minus 55.141 Newton. Nope, let's not forget the negative sign. All right, so a negative sign means that we assume that the force is acting to the right, but it's actually acting to the left, which makes sense because if we have the tension pulling in to the right at point B, then of course we have to have a force at point A pulling to the left to balance it out. All right, then the last one we have is AY. Now we got multiple ways of doing that, right? We could get AY by just saying forces in the y direction equal to 0. But again, that includes TB. But if we do the moment around B, then we don't have to worry about that. So let's do that. So we'll say sum of moments around B is equal to 0. What do we get there? Well, we get, of course, AY. That's what we're looking for. That is going clockwise, and the bar was 12 meters. So we get minus AY times 12 meters. And then we get our resultant force from the distributed load. That is turning counterclockwise. And that is 180 Newton, and then 12 minus 5.5, that's 6.75. So we get plus 180 Newton times 6.75 meters. All right, so we can, of course, solve that for AY. AY is then 180 Newton times 6.75 meters divided by 12 meters, and that gives me 101.25 meters. That will be AY. So with that, I have everything that we need. Right? We wanted the 3 support reactions, so we found them: TB, AX, and AY. We didn't use sum of forces in the y direction, so we can do a quick check. Right? We know that AY plus TBY has to be the same as R. So we said TB was 96 point something, and if we multiply that by cosine, by the sine, so 96.136 times 55 sine is 78 point something. 78 plus 101.25 gives us 180, so we're good. So with that, we did a quick check on our result. It looks good.